The exponential function discussed in the last lecture grows very, very fast. The bigger it becomes, the faster it grows. In this lecture, I'm going to discuss the logarithmic function, which, as it becomes bigger, grows slower and slower. So, in a sense, the two are inverses of each other. But what exactly is the inverse of a function, and how do you know that the inverse exists for a particular function? Let's look at that first. Let's quickly remind ourselves of the definition of the inverse of a function, and also then when that inverse might exist. So here is a number x that goes into the machine or the function g. Out comes g of x, and this number goes into the inverse function g inverse, which leads to g inverse of g of x coming out, and that has to equal to x by the definition of the inverse. Now, it's equally important that when x is put into g inverse, out will come g inverse of x, which then goes into g, and out will come g of g inverse of x, and that too has to equal to x itself. Now let me use a shorthand notation and write y is equal to g of x. In other words, when the input x is given, the output y is generated. Well, if the inverse exists, then x can be written as g inverse of y. So given y, x is determined. To make this clear, let's take a couple of simple examples. So let's say that y is equal to, let's say, 3x minus 4. In that case, x can be written as 1/3 y plus 4/3. And you see over here that x is determined by y. So we write x as a function of y. In other words, we've determined g inverse to be this thing over here. Now, that was clear enough, but what if we have something like this? Y is equal to, let's say, x squared plus 4. Well, in that case, we have x squared equal to y minus 4. And now you see that there are two possibilities. Either x can be the positive value of y minus 4 under root, or x can be the negative value. And now you see that we have a problem, because a given value of y will lead to two different values of x. And now we can understand this. Let's say that we make a little graph. Well, if y is equal to x squared plus 4, we can easily plot it. When x is equal to 0, y is 4. Let's say it's over here. And then it's going to be going up like this and equally like that. Now let's take a given value of y. Let's say y is equal to this much, whatever it is. Then you can see that there are two different values of x. This one over here and this one over here, which will lead to the same value of y. So we have to choose either this one or we have to choose this one. Both of them are different functions. And so we can say that for this function, the inverse does not exist everywhere, but it does exist to the right-hand side and it does exist to the left-hand side. So when does the inverse actually exist? Here's a theorem that's going to be very helpful. It'll answer our question. It says that suppose f of x is a strictly increasing or a strictly decreasing function, in other words, it's a monotonically increasing or monotonically decreasing function, and that's true within some interval, then the inverse exists. Now you'll say, what's the need of this theorem? Can't I always solve for x in terms of y? Answer is, sometimes you can and sometimes you cannot. If I have, let's say, y equals x to the power 12 plus 3x to the 6 plus, let's say, 2, then I don't know how to solve for x in terms of y. This is going to be too hard to do. However, this theorem is going to be very clear to understand. So here's a function that's always increasing upwards. You could call this f of x or y, whichever you like. So x increases this way, y increases that way. Within this interval, that is wherever it is monotonically increasing, if I take a given value of y, well, then I can find out what value of x corresponds to that. So here it is. This is the point here, that's x comma y. I can go both ways. I can go from x to y or y to x, and that's the meaning of the inverse. Now note also that because this function is always sloping upwards, therefore its derivative f prime is positive everywhere within the interval from here to here. One can say exactly the same thing about the function that's monotonically decreasing in this interval over here. You can see that if I give you, let's say, this value of y, well, you can then tell me which value of x that corresponds to. So this point over here is xy again, and we can go both ways. Given x, we can get to y. Given y, we can get to x. And of course, over here, the derivative f prime is negative everywhere. That's for a strictly decreasing function. But what about this? These two curves are going to be different. So let's look first over here. You see that if I give you this value of y over here, then the values of x that can correspond to that are this over here, or this over here, or this over here. So three different possibilities for x given a y, and that says that this function does not have an inverse. Well, of course, it has an interval in a shorter interval. Let's say I take this interval over here, then this is a monotonically increasing function, and it does have an inverse, but only in this interval, not in the entire interval shown over here. This curve over here is even worse. It's not even a function. Now, what does that mean? It says that if I give you x, you don't know if the value of y is this or this or this. It could be any one of those three. So x does not uniquely determine f of x or y, the three different values of y. And correspondingly, if I give you, let's say, this value of y, well, then it could be 1, 2, 3 different values of x that could correspond to that. So this is not invertible, does not have an inverse, and this is not invertible. In fact, it's not even a function. Let's apply what we've learned so far to the trigonometric functions. Look at sine of x first. This is a function that's monotonically increasing between 0 and pi by 2. And then it's monotonically decreasing between pi by 2 and 3 pi by 2 over here. You learnt in school that if you take the sine of pi by 6, in other words, if you take the sine of 30 degrees, you get half. And so you would be tempted to write
that the sine inverse, that the inverse function at half is pi by 6. That's only partly right, because really you have to state that the values of x had been limited to being between pi and 0. Sorry, pi by 2 and 0. Because if you look over here, yes, it is true that at pi by 6, at x equal to pi by 6, you get f of x as half, or sine, the value of sine is half, but also the value is half over here. So if you ask what is the value of x at which you get sine to be half, well, there's a second value. You could say sine inverse of half is now 5 pi by 6. This point over here being 5 pi by 6. Now, this answer is correct provided x is limited to these values. This value is correct provided x is limited to being less than pi and greater than pi by 2, and so forth. So the important thing is that there is no unique value of the inverse. You have to specify the domains. Now, there's a small nomenclature that you should be aware of. A lot of people call sine inverse the same as arc sine. The two mean exactly the same thing. Let's go on to the tangent. So here is f of x, which is tan of x, and tan of x also repeats. You can see it repeats over here with a periodicity, because tan of x is sine of x over cosine of x. And if you were to ask, what is the value of x at which the tangent is 1? Well, you can see that there are many, in fact, an infinite number of values at which it is 1. So it's 1 over here, and at this point you have pi by 4. Remember, what you learned was that tan of pi by 4 is 1, and so you would write pi by 4 is tan inverse of 1, or sometimes you write this as arctan of 1. But that's true only if the values of x are restricted to being between pi by 2 and 0, and so forth. You can see that there's another value here. That value is 5 pi by 4, and so forth. So again, there are an infinite number of places where the tangent is 1. We'll now consider a theorem that's very useful if you want to compute the derivative of the inverse of a function. So here's a function that has an inverse. It's because it's always sloping upwards. Because it's always sloping upwards, therefore its derivative is going to be always positive, at least in whichever interval we're considering it. And now, if y is written as f of x, then since the inverse exists, you'll write x is f inverse of y. But maybe we don't like to write inverses too much, so let's call f inverse g. So x is g of y. Okay? Let's remember what the definition of the inverse is. That definition says that the inverse acting on the function itself always gives you x. That's the definition. Now, the next point is that we're going to use the chain rule, which we learnt about a couple of lectures ago. The chain rule says that if I differentiate the left-hand side, I'm going to get g prime. And remember, this is very, very important, that derivative has to be evaluated at the argument of the first function. Then you've got to multiply by the derivative of what's inside again, and that's f prime of x. And as we differentiate the left side, we get 1. Now, f of x is what we've called y, and so therefore we've proved what we wanted to prove, that g prime of y is 1 over f prime of x. There can't be anything simpler than this. All you have to do is use the chain rule. You'll now see how easy this theorem makes the computation of some derivatives. So, for example, we've been asked to calculate this thing, g prime at 3, which means the following. It means g prime at y equal to 3, of course, or equivalently, it's the derivative of the inverse at y equal to 3. That's just amplifying what this means over here. Okay, so if y is equal to 3, then that means x cubed plus 1 is equal to 3 from above, which says that x squared, or rather x cubed, must be equal to 2, and so x is 2 to the power 1/3. Now, let's use the theorem that we just derived, which said that g prime at any value of y is 1 over the derivative of f at the point x. So let's remember that x is that point at which y has to have value 3. Okay, so we're almost there. That says that g prime at y equal to 3 is 1 over the derivative of f prime. F prime, when differentiated, gives you 3x squared. And now x is 2 to the power 1/3, so that's 1 over 3 times 2 to the 2/3. That's the answer. That was easy enough. Let's go to another problem. Here f of x is this product of 3 factors, x minus 1 into x minus 2 into x minus 3, and what we want is the value of g prime at y equal to 6. Well, when y is equal to 6, then we want x minus 1 into x minus 2 into x minus 3 to be equal to 6. And you can see immediately that when x is 4, then the left side and the right side will be equal, because you have 3 into 2 into 1. Fine. So we know the value of x at which we must evaluate. What about f prime of x? Well, f prime of x from the above is x minus 2 into x minus 3. I'm just using the product rule, and so I've first differentiated this, leaving the others 2 intact. Then I'm going to leave the first one intact, differentiate the second one, and leave the third intact. And finally, I'm going to leave this and this intact and differentiate the last one. So I have x minus 1 into x minus 2. And let's now put x equal to 4. So we have 2 into 1 plus 3 into 1. And here we have 3 into 2. So 2 plus 3, 5, plus 6, 11. And that's the value of f prime of x at x equal to 4. So this is at x equal to 4. And so we found that g prime at the point y equal to 6 is just the reciprocal of that. So it's 1 over 11. Now that we've understood what the inverse of a function means, we're going to come to the logarithm, which will be the inverse of the exponential in the following sense. Let's say that we have a number x, we put it into the exponential function, out comes e to the x, which then goes into the log function, and out comes log of e to the power x. And now, since the log is to be defined as the inverse of the exponential, this has to be x. Now, similarly, this we require just as much, that if x is put into log, out comes log of x, which then goes into the exponential function, and out comes e to the log x, and that too has to be x itself. So these are the two defining relations that you should absolutely remember, that log of e to the x is x, and that e to the log x is x itself. Now from this we make a number of deductions. First of all, let's put x equal to 0. Well, if we do that, then we have log of e to the power 0 is equal to 0. But e to the 0 is 1. And so what we've found is that log of 1 has to be 0. And that's something that's very important to remember. We'll get another important consequence. Let's say that we call y as e to the power x. And let's then take two different values of x and correspondingly the two different values of y. So y1 is e to the x1 and y2 is e to the x2. Now let me take the two values to be different. So x1 is to be taken bigger than x2. In that case, because the exponential grows with x, therefore we must have that y1 is bigger than y2. Remember that the exponential is a monotonically increasing function. And in fact, this is why we were able to define the logarithm as the inverse of the exponential. Anyway, now let's take the log of y1. The log of y1, as we see from here, is x1. And the log of y2 is x2, obviously. And so we have this relation that log of y1 must be bigger than log of y2 since y1 is bigger than y2. And that's telling us that the logarithm increases as its argument increases, and this too is a monotonically increasing function. Here is a plot of the logarithm. You see that when x is 1, then log of 1 is indeed 0. As x increases, the logarithm increases, and you see that it's increasing, but at a very, very slow rate. So in a sense, this is the inverse of the exponential, which grows so extremely rapidly. Using the fact that the logarithm is the inverse of the exponential, we're going to derive some important relations. Let's start with this one. We're going to prove that log of a plus log of b is log of the product of a times b. That's easily done. Let's call log of a something, let's call it u, in which case a is e to the power u. Similarly, let's call log of b something, v, in which case b is e to the power v. Now let's multiply a with b. So that's just e to the u, e to the v. And since these are exponents, this becomes e to the u plus v. Now, let's take the logarithm of both sides. So log of ab then becomes log of u plus e to the u plus v. And log of e to the anything is u plus v itself, which means that we have proved that log of ab is equal to log of a plus log of b. And of course, you could extend this to any number of factors. So if you had log of a plus log of b plus log of c plus etc., etc., well, this would then be log of a times b times c, etc., etc. So the logarithm of a product is equal to the sum of the logarithms. That was easily done. Now let's go on to another important relation, that the logarithm of the reciprocal is minus the log of whatever was there. So that's also very easy to do. And for this, we shall use the fact, we'll just use a little trick, that a times 1 over a is 1, of course. And so now let's take this one over here, a times 1 over a equals 1, and take the logarithm of both sides. So I have log of a, and here I have 1 over a. So I'm going to treat this as something and this as something else. That is log of a plus log of 1 over a. And that's got to be equal to log of 1, but we've just proved that log of 1 is 0, and hence we've established that log of 1 over a is minus log a. That's directly from here. Now, what this means is that if I have log of, let's say, a over b, in that case, this is log of a plus log of 1 over b. But log of 1 over b, we've just found out, is minus log b. So this is log of a minus log of b. Using the equations that we've derived, we're going to get some more interesting relations. Let's begin with a to the power n, which is a multiplied by itself n times. So n over here is an integer like 5 or 7 or 22 or whatever. Let me now take the logarithm of both sides. So log of a to the n is, here I have a product of factors. So I just take the logarithm of each one of these, and that's n of them. And so this goes on until the last one, which is log a. And there are n of these, so this is n times log of a. This relation actually tells us why the log grows so slowly. Suppose that somehow we've calculated log of 10. We haven't done it, but it's some number. Well, what's log of 1,000? The log of 1,000 is 3 times bigger. So it's 3 times log of 10. The log of a million is 10 to the 6, is just 6 times bigger. And the log of a billion, which is 10 to the 9, is only 9 times bigger than log of 10. So this tells us that the log is growing very, very slowly. Now, let's look at what we've derived. It's log of a to the n, which is n log a. And now let me give you a different form of this. A to the power n is equal to e to the n log a. Why? Well, take the log of both sides. Take the log of this, which is n log a. Take the log of this side, that's also n log a, because if you take the log of e to the anything, then by definition, it's that exponent. Now, let's ask what happens if n is not an integer. What if it's just an ordinary number, like let's say square root 2 or whatever? This relation continues to hold. A to the x is equal to e to the x log a, just like over here, where n was an integer. This then takes us to another important relation. We want to know how to differentiate log of x. Or, in other words, we want to know what is log of x prime. There is a very easy way of doing this. We only have to recall the definition. The definition of the log is that e to the log x is equal to x. And after that, let's just use the chain rule, like we did before, just a little while ago. When we differentiate the exponential, we get back the exponential with the same argument. So e to the log x, and then we have to differentiate what is the argument of the exponential. So that's log of x prime. And on the right hand side is x, which when differentiated gives 1. And so log of x prime is 1 over e to the log x. But e to the log x is x. And so this is the derivative of the logarithmic function. Or you could say d by dx of log of x is 1 over x. Now this incidentally is telling you also that as x becomes larger and larger, the rate at which the logarithm grows becomes smaller and smaller. Again, that's the exact opposite of what the exponential function does. Finally, some very interesting relations that I'm sure you will like. Let's look at this one. 1 plus epsilon x to the power 1 over epsilon. As epsilon goes to very small values, I claim this becomes e to the x. So we have something that's of this form, 1 plus something small, and multiplied by itself many times over. And this finally, I claim, becomes e to the x. Now that looks very strange, but let's see if this will work out. Well, you remember we just learned that a to the power x can be written as e to the x log a. And so I'm going to write 1 plus epsilon x to the 1 over epsilon. Using that, I'm going to write this as e to the 1 over epsilon log of 1 plus epsilon x. Now, basically what I need is the limit as epsilon goes to 0 of log of 1 plus epsilon x divided by epsilon. This is exactly the situation for which we had developed L'Hopital's rule. So the numerator is going to 0, the denominator is going to 0. Let's differentiate the numerator. If we differentiate the numerator, that becomes 1 plus epsilon x. But remember, we've got to differentiate the numerator with respect to epsilon, not x. And so we get x as well. If we differentiate the denominator, we get 1. In the limit, as epsilon goes to 0, this becomes x. Now, what we've shown, therefore, is that 1 plus epsilon x to the power 1 over epsilon then goes to e to the power x, which is exactly what we wanted. Let's use that same trick to find the derivative of a function which has this weird form, g of x to the power h of x. So let's get, first of all, rid of the x's. It's understood that they're there, but we don't want to keep writing them. So g to the power h. If we take this to have, well, let's now use the different form that we've used before. This is e to the h log g. And now we can write f prime by first differentiating the exponential. So I'm now using the chain rule again. And if I differentiate the exponential, I have to take the derivative at the argument which was originally there. Now I need to differentiate the argument of the exponential. So that's h log of g prime. After that, it's pretty straightforward. E to the h log g is g to the h. That's how we rewrote it. And then we need to differentiate this. This is h prime log g. And then we don't do anything to h. We differentiate log of g. If you differentiate log of g, first of all, you get 1 over g. And then you've got to differentiate the argument by the chain rule. So that's g prime. And that is the final answer.
The exponential and logarithmic functions discussed in this lecture are examples of smooth functions. And smooth functions can be approximated as closely as you like by polynomials. This is going to be the content of Taylor's theorem, which we shall discuss next time.